The lifting products industry manufactures a wide range of equipment essential for heavy-duty operations across construction, shipping, mining, and industrial sectors. Annually, over 1.2 million tons of lifting slings, chains, and ropes are produced globally. The market for lifting equipment was valued at $78 billion United States dollars in 2023, with projected growth to $102 billion United States dollars by 2028, driven by increased infrastructure development and safety regulations. High-tensile alloy steel chains and polyester slings are produced in varying load capacities, from 500 kilograms to over 100 tons, ensuring compatibility with cranes, hoists, and rigging systems across all lifting applications. Group produces heavy lifting equipment by designing, manufacturing, testing, and certifying steel wire and fiber rope slings. Protection, called point station side. Fabricating a 3-inch wire rope sling involves measuring and cutting the rope, preparing and securing the ends with fittings, and applying swaging or socketing techniques. The process ensures durability and safety, followed by a thorough inspection to verify compliance with industry standards before use in lifting applications. For those working at sea, braiding ropes might seem like a simple task, but it can be a matter of life and death. Properly braided ropes can withstand immense loads without unraveling, which is crucial during docking operations, especially at sea. Docking two vessels in open waters is a labor-intensive and high-risk operation, where even a small mistake can lead to significant delays or hazards. A poorly braided rope can create a dangerous situation, where the free end of the rope increases the load on the remaining strands, potentially causing them to break. This could lead to a delay of around 4 hours to prepare a new attempt, but the risks are far more severe. A snapping rope under tension can be catastrophic, with the potential for serious injury or even death. The video showcases the importance of correct braiding techniques to ensure the safety and efficiency of marine operations. It emphasizes the skill and precision required to ensure the rope holds under immense pressure during docking maneuvers, preventing accidents, and ensuring vessels remain securely connected. Furthermore, proper braiding enhances the lifespan of the rope, making it more durable for repeated use. Properly prepared docking lines can save lives and prevent costly damage to vessels. Siemens Energy's Competence Center for Energy Transition Technologies in Mulheim, Germany, plays a pivotal role in producing large-scale electrical generators designed to power the future. The manufacturing process begins with the inductor, which is the rotating part of the generator, where mechanical energy is converted into electrical energy. The conductors are inserted and soldered, followed by quality checks using ultrasound. In parallel, the stator, which is the stationary part of the generator, is created by stacking over 100,000 sheets, forming a laminated core. After welding, the stator is rotated, and the winding bars are installed. The assembly progresses with impregnation of resin, ensuring durability and structural integrity. The inductor is then processed with rigorous checks. Once both components are prepared, they undergo the marriage phase, where the inductor is placed inside the stator. The generator is then subjected to extensive testing before being delivered to clients. The production of drill bits at Minnesota Twist Drill begins with receiving coiled steel, which is straightened and cut to length. Heat treatment hardens the steel, followed by grinding to achieve precise dimensions. Fluting, clearance grinding, and pointing shape the bit. Finally, the bits are marked, packaged, and prepared for shipment to customers. The production process at China Osram Electric Motor Company is highly automated, ensuring efficiency and precision in motor manufacturing. First, stator winding is performed automatically, with copper wire carefully coiled around stator cores. These windings are then bound securely to maintain structural integrity. Large steel plates are cut and stamped to create essential motor components. CNC machining ensures precise shaping of parts. Next, robotic welding is used to attach electrical terminals, guaranteeing strong and consistent connections. The automatic assembly line integrates the stator, bearings, and other motor components. Laser processing is applied for precision cutting and marking. Blower motors and other units are tested rigorously to ensure they meet quality standards. Small motors are queued for testing before packaging. Finally, fully assembled motors are incorporated into products such as home heaters, completing the production process. This streamlined workflow, combining automation and quality control, ensures high-performance electric motors for various applications. The repair and rewinding of an electric motor involve a meticulous process to restore its efficiency and longevity. The procedure begins with an initial inspection, where electrical tests, such as insulation resistance and surge testing, help diagnose faults in the windings. Once faults are identified, the motor is disassembled, and critical components like bearings, stator, and rotor are examined for wear or damage. If the winding is defective, the old coils are removed by carefully cutting and burning off the insulation without harming the core. Next, the cleaning phase ensures that dirt, oil, and debris are removed using abrasive blasting. A fresh layer of insulation coating is applied before inserting new windings into the stator slots. These new coils are meticulously wound and secured, maintaining precise turns and wire dimensions. After winding, a series of electrical tests confirm the coil's integrity before it undergoes a vacuum impregnation process using insulating varnish. The stator is then oven-baked to solidify the insulation. Meanwhile, the rotor undergoes balancing to reduce vibrations and enhance smooth operation. Finally, the motor is reassembled, fitted with new bearings, and subjected to a load test to verify its performance before being delivered for industrial use. This comprehensive approach ensures the restored motor functions reliably with enhanced efficiency. The process at LAPP Group follows strict quality standards to ensure durability and efficiency. It begins with raw material preparation, using high-quality copper or aluminum conductors. The metal is drawn through dies to reduce its diameter, then annealed for flexibility. Stranding machines braid multiple wires together before extrusion coats them with PVC or XLPE insulation. Cables are then assembled, shielded, and covered with protective sheathing. Finally, rigorous quality tests check electrical conductivity, tensile strength, and environmental resistance. The production process of bolts, using the automatic cold thread rolling machine by Industrial Machinery Corporation (IMC), begins with selecting the raw material, typically steel wire or rod, which is cut into the desired lengths. The material then undergoes the heading process, where it is subjected to high pressure in a cold heading machine to form the bolt's head. Once the head is shaped, the bolt is passed through IMC's automatic cold thread rolling machine, where threads are precisely formed on the bolt's shaft using rolling dies. This cold thread rolling process strengthens the bolt by aligning the metal's grain structure, making the threads durable and smooth. After the threads are formed, the bolts are cut to the required length, and optional heat treatment may be applied to enhance their hardness and tensile strength. The bolts then undergo a surface finishing process, such as plating or galvanization, to prevent corrosion. Throughout the process, quality control checks ensure that the bolts meet the required specifications for size, strength, and finish. Finally, the finished bolts are packaged for shipment. This section is about the production process of the 4.5-liter Saturno pressure cooker. First, the design phase begins with the creation of a 3D model using CAD software, which specifies all technical parameters, including dimensions and safety features such as pressure release valves and locking mechanisms. Once the design is finalized, it is converted into G-code through CAM software to guide the CNC machines during the manufacturing process. In the preparation stage, high-quality stainless steel, typically conforming to ASTM A240 standards, is selected. The steel sheets are then cut using a laser cutting machine with a 1500 W power capacity, achieving an accuracy of plus or minus 0.1 millimeters. These sheets are subsequently shaped and stamped using a 200-ton press to form components like the body and lid. TIG welding is employed to securely join the parts together, ensuring a robust and aesthetically pleasing finish. Once the components are welded, the assembly process begins. Parts such as the handle, safety valve, and rubber seals are carefully installed. The handles are attached using M6 bolts, ensuring durability. The final pressure cooker is subjected to a rigorous quality check, including a pressure test at 1.5 times the working pressure to ensure there are no leaks. The last steps involve surface polishing, where the food contact surfaces are polished at a speed of 3000 RPM for a smooth finish. The cookers are then packed into boxes, dimensions 30 by 30 by 30 centimeters, with 5 units per box, and shipped with instruction manuals and warranties to ensure customer satisfaction. This process guarantees that each Sachin pressure cooker meets high standards of quality, safety, and efficiency. The production of rolling mills at the Lipetsk plant plays a vital role in producing metal profile products like corrugated sheets and metal roofing tiles, which are essential in modern construction. Since 2004, the Lipetsk Profile Bending Equipment Plant has been designing and manufacturing rolling mills for processing flat metal sheets. These mills are known for their high productivity and delicate handling of materials. The profiling process involves passing smooth metal sheets through a series of rolling mill stands, which gradually shape the material. For metal roofing tiles, the sheets undergo stamping at specific intervals and are then cut into required lengths. The production of rolling equipment begins with cutting raw materials into blanks. These blanks are then mechanically processed to create components for the rolling line. One of the key parts is the rolling shaft, which holds the profiling rollers, and each rolling mill contains over 2,000 parts like bearing housings, stands, supports, and clamps, all carefully machined and assembled. After welding the frames, they are painted before final assembly. An important component is the coil unwinder, which ensures proper sheet feeding. The profiling rollers are manufactured with precision and are securely attached to a shaft. Once all parts are ready and painted, final assembly begins, including the installation of the upper and lower rollers, which are temporarily fixed before fine-tuning. The rolling mill is then painted again. Guillotine shears are added to cut the finished profile into sheets. These blades are precisely manufactured, and any deviation can lead to uneven cuts. The blades are heat-treated for durability and bolted to the shear frame. After assembly, final adjustments are made, ensuring proper alignment and clearance between the rollers. The electrical system, including wiring, terminals, and drives, is connected, and the control panel is installed. The rolling mill undergoes calibration, ensuring it operates smoothly. Once the system is fully tested, the mill is ready for shipment. The coil unwinder, rolling mill, guillotine shears, and automation system work together as a single rolling line, which is then shipped to customers. The dedicated team at the Lipetsk Profile Bending Equipment Plant manufactures these complex machines daily, delivering high-quality rolling mills for industrial applications. For over 100 years, Survey has been a leading supplier of power and motion control solutions, specializing in the design and production of valves, valve blocks, cylinders, accumulators, and HPUs. Located in Rissa, Norway, just north of Trondheim, the company uses advanced design tools and simulation software to develop efficient and high-quality solutions. Survey focuses on environmentally friendly practices, utilizing heat pumps for energy efficiency and minimizing CO2 emissions. With a long history of in-house hydraulic production, the company manufactures hydraulic cylinders with piston diameters from 20 to 2,000 millimeters and stroke lengths up to 20 meters, adhering to offshore standards and customer requirements. Siemens specializes in manufacturing and maintaining mechanical components for the sugar industry. The production process begins with design and engineering, where technical drawings and 3D models are developed. In metal casting, advanced techniques produce durable components. These parts undergo precision machining using CNC technology for cutting, drilling, and shaping. Rigorous quality control ensures strength and dimensional accuracy. After machining, components are assembled and finished, including corrosion-resistant coatings. The final step is testing and inspection before shipment. Siemens also offers after-sales services, including maintenance and technical support, ensuring long-term efficiency. Combining modern technology with expertise, Siemens delivers high-performance solutions for sugar mills, optimizing production and operational reliability. Mannesmann Line Pipe specializes in producing longitudinally HFI-welded steel tubes and pipes. The process begins with steel strips, typically 3.5 mm to 12 mm thick and 250 mm to 600 mm wide, with grades ranging from X42N to X80N. The strip is formed into a tube and heated through high-frequency induction to around 1,600 degrees Celsius. The edges are then welded using HFI technology, followed by flash removal from the internal and external surfaces. The welded pipe is heat-treated, straightened, and sized to precise specifications. Pipes, ranging from 114.3 mm to 508 mm in diameter and 4 mm to 20.6 mm in thickness, are tested for pressure resistance, ensuring their integrity for applications like oil and gas transmission. The production of Worthington X-Series steel scuba cylinders begins with the preparation of high-grade chromoly alloy, which meets strict requirements for grain structure, impurity levels, and micro-cleanliness. The raw material undergoes deep drawing and ironing operations, using up to 800 tons of force in the first press and 250 tons in the second. The deep drawing process reduces the material's diameter and thickness by 60% in each draw, typically performed 3 times. Afterward, the open end of the cylinder is trimmed and subjected to ultrasonic inspection. Next, an oxygen fuel gas torch heats the cylinder to approximately 1,600 degrees Fahrenheit, and the hot spinning process forms the upper portion of the cylinder using CNC technology. This process ensures a uniform, high-quality shoulder and neck profile. Following heat treatment in a computer-controlled furnace, the cylinders are machined to add internal threads and O-ring grooves. They undergo hydrostatic testing, with cylinders pressurized to 5/3 of the service pressure. After testing, the cylinders are cleaned, shot blasted, and coated with a corrosion-resistant primer, followed by hot dip galvanizing for added protection. Finally, they are marked with regulatory information and packaged for shipment. The steel casting production process begins with the preparation of raw materials, like iron ore, coke, and limestone. These materials are fed into a blast furnace, where they undergo a chemical reaction to produce molten iron. The molten iron is then transferred to a refining furnace, such as the basic oxygen furnace, BOF, to remove impurities and adjust the composition. The steel is cast into molds using continuous casting or sand casting, and further processes like heat treatment and machining shape the final product for use in various applications. OI New Zealand. the country's only glass manufacturer, operates 6 production lines 24/7. The process begins with raw materials such as recycled glass, soda ash, lime, and limestone, with over half being recycled for sustainability. These materials are loaded into hoppers and fed into the furnace, where they are melted at 1,600 degrees Celsius to form molten glass. The molten glass is then cut into gobs and moved to the blank side of the machine, where it is pressed or blown into a parison. The parison is then transferred to the mold side of the machine, where it is blown into its final shape, like beer or wine bottles or jars. Lubrication is key to smooth operation, using special oil with high graphite content to reduce friction and maintain proper machine temperatures. Mold maintenance is critical, as wear can cause defects. Molds are repaired by spraying metal particles onto damaged areas, which are then ground to precise dimensions. Plungers, which form screw-top areas on bottles, are reprofiled when worn to ensure quality. Safety is a priority as employees work with molten glass and hot machinery. Protective gear is essential for safety in high-temperature environments exceeding 1,600 degrees Celsius. The entire process is closely monitored to maintain consistency and ensure the highest quality of glass products. Malcolm Drilling specializes in cutting-edge ground improvement techniques. Their triple auger soil mixing process blends cement with in-place soil using synchronized rotating augers to form strong, stable columns. For large-scale projects, mass ground improvement densifies weak soils through deep mixing and heavy equipment. Their oscillator shaft system drives massive casing sections through dense ground layers, enabling deep foundation work without vibration. These advanced methods are designed to enhance load-bearing capacity, reduce settlement, and support complex infrastructure on even the most challenging terrain. Meet the Volvo PL 4611 pipe layer, the future of pipeline construction. Working on Germany's Bunde-Etzel pipeline, this revolutionary machine combines 360-degree swing capability with exceptional maneuverability, thanks to its excavator-based design. A cutting-edge load management system ensures unmatched safety during lowering operations, keeping the machine stable even under extreme weight. With removable track frames, it's easily transported without special permits. The elevated cab provides excellent visibility, allowing precise control of 12-ton pipes. Contractors like GSN praise its performance, lifting up to 1 kilometer of pipeline per day. With power, flexibility, and speed, the Place 4611 redefines productivity in pipe laying, turning Volvo into a game-changer for the entire industry. Step inside the process of manufacturing durable precast concrete road panels with this advanced machinery system. The system begins with a pre-stressing cable launcher that moves along the track, laying down pre-stressing cables. Transversal spacers are placed to define the panel's length, and one end of the cables is locked in position. Next, the concrete distributor machine is positioned over the track, distributing concrete evenly and rapidly. Vibrating screeds compact the concrete along the track, ensuring a smooth finish. This complete system guarantees the efficient production of high-quality concrete road panels. The Perfect Block Company is revolutionizing green building with their insulated composite concrete forms, ICCF, made from 100% recycled materials. With a temperature tolerance of up to 4,000 degrees, these blocks measure precisely, ensuring perfect cuts and easy installation. Beam seats fit seamlessly, and grout flows smoothly for efficient construction. The production process is enhanced by mobile manufacturing plants, providing low-cost, high-efficiency production. The Trans-Adriatic Pipeline, TAP, spans 495 kilometers, carrying natural gas through 48-inch steel pipes manufactured by Corinth Pipeworks. Let's take a closer look at the thorough process of constructing this vital energy infrastructure. The first step is clearing a 28-meter-wide right-of-way row along the pipeline's route. The land is leveled, and the topsoil is carefully stored for later reinstatement. Truckloads of 48-inch steel pipes are delivered to the designated work zone. Each pipe is laid end-to-end along the route. Specialized equipment bends the pipes to match terrain variations and directional changes. Above ground, skilled welders fuse the pipes together. Every weld undergoes automated ultrasonic testing to ensure structural integrity and compliance with rigorous safety standards. Each welded joint is grit blasted and coated with protective layers. This process prevents corrosion and shields the pipeline from mechanical stress. A trench is carefully excavated, keeping the topsoil separate for future restoration. Side boom tractors gently lower welded pipe sections into the trench. Up to 1 kilometer of pipeline can be positioned at a time. Pipe sections within the trench are welded together to form a continuous pipeline. Fine soil is placed around the pipe for protection before the trench is refilled with compacted subsoil and the original topsoil. Finally, the right-of-way is restored as closely as possible to its original condition. Erosion control structures and additional topsoil help encourage vegetation regrowth and soil stability. This diligent process ensures the secure and efficient transport of natural gas, supporting Europe's energy network. The pipeline relocation at Smoky Lake is a precise and methodical process, especially when moving an operating pipeline. With the goal of moving a 5-year-old pipeline, while it remains pressurized, this model excavation covers 3 city blocks. The careful work requires excavation at 15-meter intervals, ensuring the dirt is piled back to minimize risks. Once ready, the pipeline is gently moved, using slings rated for multiple times the required weight, with 4 machines working in tandem to move the pipeline 1.2 meters over. This procedure ensures minimal stress and a smooth operation. Though it may appear slow, the entire pipeline is relocated in approximately an hour and 45 minutes. Moving the smaller 16-inch line away from the larger 24-inch line allows work to continue on the latter. The next steps will involve filling in the excavation and preparing for the hot tap and stopple bypass for the new Smoky Lake pump station, marking a significant milestone in the pipeline's operation, ensuring stability and safety in buildings, bridges, and large-scale infrastructure. The process begins with interpreting blueprints and marking positions for structural components. Heavy steel beams and columns are lifted into place using cranes, guided by ironworkers using hand signals. Once positioned, the components are temporarily bolted together before precise adjustments are made. High-strength bolts or welding techniques secure the structure, ensuring durability. Workers use tools, such as impact wrenches, torches, and welding equipment to fasten steel components. Safety is paramount, requiring harnesses, safety nets and protective gear, as they often work at great heights. Ironworkers also install reinforcing bars, rebar, in concrete structures, enhancing load-bearing capacity. Advanced technology, including robotic welding and automated cutting systems, improves precision and efficiency. The teamwork, skill, and precision of ironworkers contribute to creating the modern skylines of cities, making them essential to the construction industry. The erection of a major steel beam at the roof of the atrium in the Leslie Dan Faculty of Pharmacy required careful planning and precise execution. A 50-ton full-story truss was lifted to the 5th floor and positioned on a slender concrete atrium. This truss was crucial for suspending a classroom pod within the space below. The alignment process was highly detailed, ensuring the truss connected correctly to a vertical slip joint, a beam at 1/3 of its length, and a column at the end point. Skilled ironworkers managed the process, securing the structure for stability. This project demonstrated the importance of precise fabrication, constructability considerations, and structural integrity in complex architectural designs. The painting process of MSC Meraviglia in August 2016 involved applying 300,000 liters of paint. The ship's surface was cleaned, sandblasted, and primed for corrosion resistance. Anti-fouling coatings were applied below the waterline, while decorative layers completed the design. Quality checks ensured durability and aesthetic precision. The KCM 250 is a high-speed, fully automated machine designed for wire drawing, thinning, pressing, and cutting, ensuring precision and efficiency in metal processing industries. Equipped with a powerful 130 kilowatts motor, it operates at an impressive speed of 250 meters per minute, allowing for continuous, high-output production. The machine utilizes an adjustable twist control system, offering precise roller-based adjustments for enhanced wire shaping and quality control. For material handling, the stacking system supports a standard length of 6.80 meters, with an optional extension of up to 12 meters to accommodate different production requirements.